Good morning, students. Today we will discuss about the pneumatic controllers. In last class we have covered control actions based on different modes of control actions. That means on-off control action or two-step, and others are continuous control actions. And I mentioned that in next class we will cover the mathematical modeling. But before starting the mathematical modeling of processes, I think we should cover the controllers. Pneumatic controllers again are of depending on type of energy. That is, if the operating energy is pressure signal, then that is pneumatic controller, and other is electronic controller operated by electronic signal or electrical signal. In today's class we will cover pneumatic controllers. Pneumatic controllers mainly based on flapper nozzle system. You are familiar with flapper nozzle system. All pneumatic systems, maybe controller or other devices, the basic units are flapper nozzle system and relay. And the different types of pneumatic controllers are self-operating controller, motion balance type controller, and force balance type controller. Self-operating is purely a typical type that is based on its own action. That's why this is called self-operating controller. And other two types are motion balance type and force balance type. These two actually the two major types of pneumatic controllers. One is motion balance type, that is based on motion of a balance beam, and force balance type, the pressure balance on the diaphragm, separated by two or more pressure chambers are separated by diaphragm, and the force balance on the diaphragm, that is the principle of controller. So two major type of pneumatic controllers are motion balance type controller and force balance type controller. Now the fundamental is the pneumatic type controllers based on flapper nozzle systems, and the one is self-operating type controller. This is these two are the examples of self-operating type controller. This is called flow type air pressure regulator, and this is dead end type air pressure regulator. Why this is called flow type? See, the flow path is this one. I think you can follow the flow path. This is the pressure or air signal input through this path, then flows through this and goes out from the chamber through this path. So this is the flow path of the airflow. And here is a diaphragm that is balanced on by a spring balance. This is the set point knob, that is the desired pressure which is to be set on the diaphragm is set by the set point knob through the compressor spring. And what will happen when pressure flows or air flows through this path, then a balance on the chamber, pressure balance on the chamber or the pressure balance on the diaphragm should be maintained. That is the pressure set by the set point knob, that is the downward pressure to the knob. The downward pressure to the knob is set by the set point knob, and the upward pressure to the knob to the diaphragm, the upward pressure to the diaphragm is the pressure of the flowing air on the diaphragm. Now see, if the outlet flow get restricted due to certain reasons, say the restriction provided at the outlet path, then what will happen? That means the inflow remains same as previous and the outflow get restricted. Then the pressure within the chamber will increase. That means the upward thrust on the diaphragm will be more than that on the of the downward force. As a result, the diaphragm will try to move upward. And see, this is the valve, and valve is again connected by a restoring spring with the body of the lower portion of the body. So the valve will move upward when the pressure inside pressure of the chamber will rise above the set pressure. Then what will happen? This plug will try to move upward. As a result, this restriction, this flow path will be restricted. That means the inflow will be restricted. So the flow rate will decrease. So when the outflow get restricted due to certain reason, the inflow will be controlled by its self action. That's why this is called self-operating type. I think I am clear about this, that this is the airflow path through this, and if the outflow get restricted due to certain reason, then what will happen? The inflow remains same, but the outflow gets restricted. That means the inside chamber pressure will rise above the set point pressure. So as a result, the diaphragm will try to move upward direction, and so the plug that is connected with the diaphragm will also move towards upward direction. As a result, this path will be restricted. That means the inflow will be allowed less. So when the outflow requirement is less, it will be, the inflow will automatically controlled by its own action. That's why this is called self-operating type. The electrical analogy of this is the PI. The electrical model is through this variable restrictor, as this is variable, so this is the variable restrictor, and a fixed restrictor R1, since there is no valve or no control over there. So this is R1 and the output is P0 through the load. Again, this is variable. As the load changes, accordingly the this will be varied and PI will change accordingly, and the relationship of this is like this. The electrical analogy. This is called the flow type air pressure regulator, where the output is open end type, and this is the dead end type. Dead end type means the difference is when the outflow goes to an enclosed chamber. This is like this is the inflow path. Again, through this path and through this goes to the outflow. Like this system, this is not the open to atmosphere, rather this is open to some enclosed chamber, like the pumper of a bladder or cycle tire, like this, where the outflow goes to an enclosed chamber. For this, the difference is, again, this is the pressure balance on the diaphragm through set point knob, more or less similar structure. Only difference is the relief port exists at this portion. That means when the pressure within the chamber should decrease or should control, the relief port should open so that the pressure can be released. Since this goes to the enclosed chamber, so the pressure increase within the within this chamber should be released through some outlet port, that is the relief port. This is the example of the pump, cycle tire pumper or bladder pumper, like that. The electrical circuit, analogical circuit is this is the variable restrictor, and here is a fixed restrictor through which this goes, and the outflow is P0. So the electrical analogy P0 is inflow by the total resistance, that particular resistance by total resistance, R by R1 plus R, and as R varies accordingly, the P0 will vary with reference to Pi. And the example of this system, flow type air pressure regulator, is the pressure regulator used above the gas cylinder. This is the this is open to the burner. That means when we put the gas to seam position, from full flame to seam position, that means we are putting some restriction at the outflow. Then this pressure regulator controls the inflow, decreases the inflow accordingly, so that the pressure within the chamber can be maintained. That is due to its self-operation. This is called the self-operating type controller. This is the example of here is the internal relief port. This is the actual diagram of the cross-sectional diagram of dead-end type regulator. This is taken from some manual. Advantage of pneumatic control system controller, major advantage is this is intrinsically safe. As this is purely pressure operated, then this is no electrical hazard is there. This is they are intrinsically safe and can be used in hazardous atmosphere. This is cheap compared to hydraulic system, because that is air operated and hydraulic system is oil operated system, and that causes maintenance also due to grease. A pneumatic actuator can generate more torque of its to its own weight, and thus have a better torque weight ratio compared to an electrical actuator. That is another major advantage of pneumatic system, that is that torque generated due to its own weight is more, and better torque weight ratio can be maintained than electrical actuator. However, pneumatic components are slow in response. That is the disadvantage. Since this is air operated, so slow responding system. Now the basic units of controller, pneumatic controllers, are flapper nozzle systems and amplifier, pneumatic amplifier. Flapper nozzle systems, you are familiar with flapper nozzle system, where a flapper is a beam, pneumatic motion beam, placed in front of the nozzle chamber, and the nozzle is supplied with a constant air supply that get restricted in flowing through the nozzle diameter which is much less compared to this restrictor. So when air flows through this, and that depends on the distance between the nozzle and the flapper, that means the flapper nozzle distance is important. As flapper moves towards the nozzle direction, then the air flow passing through the nozzle gets restricted, and it gets deflected partially and goes to the, so this is called the nozzle feedback pressure, and it goes to the next chamber. Here generally a pneumatic relay is connected. So this is called the nozzle feedback pressure, and that is utilized for control action. Let's the supply pressure PS and the output pressure P0, and the diameter of the restrictors are D1 and D2, and the flapper nozzle distance is XI. Then the volume flow rate through the fixed restrictor, that means from the first one is Q1 is equals to K pi D1 square by 4 root over of PS minus P0, that is the pressure difference, Bernoulli's principle, root over of PS minus P0. PS is the supply pressure and P0 is the output pressure. And Q2, that is the flow rate, volume flow rate through the nozzle outlet, that is the diameter is D2, K pi D2 into X. Here the X is the flapper nozzle distance. That matters, since if X changes, then the outflow rate will vary accordingly. So Q2 is K pi D2 X root over of P0 minus 0. Since it's open to atmosphere, so the pressure is 0. Pressure difference is P0. Since air leaked to the atmosphere, and the distance is dia is D2 and length flapper nozzle distance is X. Now at steady state, when that flows uniformly, then at steady state this Q1 is equals to Q2. So putting this equals to this and equating from this, the relationship between P0 and PS is 1 minus 16 d2 square x square by d to the power 4, and the higher orders are neglected since the values are very small, d2, d and x, all are small parameters, and the higher orders will negligibly small. So P0 is related to the PS in this way, and the characteristics of P0 to X, that is that flapper nozzle distance, is related like this. This is the response characteristics, and the this is the 3 psi, and this scale is given in psi, and this is 15. This 3 to 15 range is more or less linear range. So we will treat this range as the linear scale, and rest portions are non-linear. So this linear scale is treated as the operating range, and that's why the range of controller is called 3 to 15 psi or 1 to 4 kg per centimeter square. Next is pneumatic relay. The first part of this pneumatic controller is flapper nozzle unit. Major limitation of flapper nozzle amplifier is its air handling capacity. Since the variation of air pressure obtained cannot be used for any useful application unless air handling capacity is increased. Since the dias are very less and the distance is also less, so the it cannot handle much pressures. So the signal is very low signal. An air relay is connected along with this flapper nozzle system to enhance the volume of air, that is to amplify the volume of air. That is the pneumatic relay. So this is the only this portion is flapper nozzle unit, and the flapper nozzle feedback pressure goes to an enclosed chamber, that is called pneumatic relay, in order to enhance the signal. Again, this pneumatic relay are of two types: direct action type and reverse action type. The name signifies its application, that direct action type means when the air supply increases, the output also increases. That is the direct action type. And reverse action type, when the air input increases, the output decreases. That is the reverse action type. Depending on type of application requirement, this direct action type and reverse action type relays can be utilized. The structure of direct action type relay is like that. The air supply, the same air supply which goes to flapper nozzle unit. See, this is the flapper nozzle portion. This is flapper in front of nozzle, and the restrictor, this is the air supply. And same supply, this is normally 1.4 kg per centimeter square, that goes to the flapper nozzle unit, and the same supply goes to the relay unit. And this is the valve or piston connected to the diaphragm, and this is the nozzle feedback pressure which goes to the enclosed chamber or pneumatic relay. This nozzle feedback pressure, that means this is the flapper unit where the nozzle flapper goes towards the nozzle direction. The nozzle feedback pressure increases, and that increased pressure goes to the relay unit. Then what will happen? As the pressure increase to this portion, then the diaphragm pressure toward upward direction will increase. The diaphragm pressure to the upward direction will increase. As a result, the valve or piston will move upward direction, and this is the seat area. Notice that this is the seat area. So when this plug will move towards upward direction, that path will be closed, and what will happen? That means this will becomes closed, but this path will get opened, right? This path will get opened. Since this plug will move upward direction, see, as this plug will move upward direction, this portion will get opened. That means the air supply will allow more through this path, that is the P out, that is the output of the relay unit. So as the input pressure increases, then the input increases means input on the flapper unit increases. That means the nozzle feedback pressure increases. As a result, the output pressure from the relay unit will also increase. That is, this is called the direct action type. And what will happen for reverse type? That means when the input pressure decreases, that means input pressure decreases means, or this flapper moves away from the nozzle direction. When this flapper moves away from the nozzle direction, that means the nozzle feedback pressure will decrease. As the pressure of this chamber will decrease, that means the diaphragm will get contracted to the inward direction. As a result, this plug will move downward direction. So when the plug will move downward direction, then again this portion get restricted. So the pressure signal which is coming from this supply path will get restricted to flow through this path. So as the pressure decreases, input pressure decreases, as a result the outflow pressure will decrease. So this is called the direct action type. And for direct action type, when input pressure increases, the outflow will also increase, output pressure will also increase, and when input pressure decreases, the output pressure will decrease. Reverse action type relay is just the reverse type. That means when the nozzle feedback pressure, this is the structure, the nozzle feedback pressure will come to the piston through the feedback relay. This is the air feedback relay. So when the pressure increases to this chamber, the piston will move towards right, and that will restrict the outflow path. This is the outflow path because this is the supply pressure. So this piston will close the outflow path. So when the input pressure increases, the output pressure decreases. This is the reverse action type. Now depending on type of application, we should use the direct action type or reverse action type relay. Next is two major type of pneumatic controllers are motion balance type. One is self-operating type, that is purely by its own action, and other two major types are motion balance type and force balance type. Motion balance type controller is based on the motion of a beam. Say this is the motion beam here, this is the motion beam, and this beam will operate rather behaves as a flapper unit in front of nozzle. This is the nozzle, and this beam is a motion beam and acts as a flapper towards the nozzle, in front of nozzle. Say this motion beam is connected with the bellows unit through which the input signals and feedback signals are connected. Say the input signal goes through this bellow to the motion beam. If the input pressure increases, then the motion beam is balanced by a fulcrum, or motion is controlled by with respect to this fulcrum. So when the input pressure increases, then initially suppose this is at balance position with reference to fulcrum. If the pressure at the input bellows increases, then the downward pressure will increase to this side. As a result, the upward pressure, this side of the motion beam will move upward direction, and this behaves as a flapper moving towards nozzle direction. So nozzle feedback pressure will rise, and that goes to the pneumatic relay. This is the relay output. So pressure output will change accordingly. Again, it depends on whether it is direct action type or reverse action type relay. It depends on the bellows positions, those are controlling signals. So there are several factors, but the principle is the motion of this beam will change the nozzle feedback pressure, and accordingly the controller output will change. Now, based on this motion balance principle, we may design on-off control as well as the continuous controllers. Say for on-off controller, the motion beam is again, this is the flapper unit and this is the nozzle and relay unit. This motion beam is connected at the end with two bellows. One is input signal bellow and the other is the one is this is the both are input bellows. One is set point bellow and other is the measured signal bellow, rather the process variable input bellow. So when the set point and measured value is same, that is in steady state or balanced condition, the this is at zero deviation position. Now if the measured value increases over the set value, then what will happen? The upward pressure at this end of the motion beam will rise. As a result, with respect to this fulcrum, the other end will move downward direction, right? So the flapper will move away from the nozzle direction. As a result, the nozzle feedback pressure will decrease. So depending on the relay type, say if it is direct action type relay, the output pressure will decrease. So when the measured value increases over the set value, the controller output is off, and the reverse, when the measured value goes below the set value, that will on. This is off state and other will be on. So this is the on-off type motion balance type control. Now for motion balance type proportional controller, just eliminate this side pneumatic bellow. This is the integral bellow. If we consider, just eliminate this portion for proportional controller, motion balance type proportional controller. See, this is the motion beam. This portion is eliminated from the pneumatic proportional controller. The measured value is input through this bellow element, and this is the set point bellow, and this is the motion beam. This behaves as a flapper towards the in front of nozzle. Now when the measured value increases above the set value, what will happen? At point C, the pressure to the motion beam will be at rightward direction. When measured value is more than set value, the pressure to the point C of the motion beam is towards right. At that point, there is no pressure change at this bellow element. So A, that is the upper point, is at fixed position. So with reference to this A, this portion of the motion beam will move towards right. As a result, the flapper will move towards right to towards the nozzle direction, and the nozzle feedback pressure will rise. Then what will happen? The pressure slowly increase to the bellow element. Then the pressure at this point, that means at point A, will increase. Then at that time, that means after certain time delay, the A will move towards left. At that time C will act as pivot, since there is no change in pressure signal. So when A moves towards left with reference to C as pivot, B will move towards left also. So the flapper will move towards the leftward direction, that means away from the nozzle direction, and the pressure will nozzle feedback pressure will decrease. So in this way the motion beam will oscillate in front of nozzle, so that the controller output changes accordingly. This is the proportional type controller. Now just get refreshed. For PI controller, now we should consider this part also. Up to this, the proportional control action is there. Now here another restrictor is there, and so when the pressure to the bellows element increases, to this bellows element increases, the through this restrictor, after certain time delay, the other side pressure, bellows element pressure, will increase. So again, when this pressure will build up, the A will move towards right, and C at that time will act as pivot. So B again will move towards right. So again the pressure at this that means when this flapper will move towards nozzle direction, so the nozzle feedback pressure will increase. So this behaves as a integral effect. So 3-step operations is there, just trying to explain once again. First is when the input signal increases, then B moves towards B1, A at that time acts as pivot, C will move towards C1, just check, where due to increase of input signal, that means when measured value goes above the set value, C will move towards right, B also move towards right, A act as pivot for that time, right? Next is this, since there is no restrictor, so the pressure will slowly rise at this chamber, but since there is a restrictor, this pressure this bellows element pressure will rise after certain time delay. A, in the next step, A will move towards left, B also move towards left. At that time, C acts as pivot. A moves towards A dash, C moves towards C dash or C2, and B at that time acts as pivot. Next, the pressure at this chamber will rise after certain time delay. That time delay is the RC time delay, RC time lag. There's this restrictor R and the capacitance of this bellows element C. So after the time delay, A will move towards right, B also moves towards right, C at that time acts as pivot. ABC that should be C. Okay. Anyway, the midpoint is flapper point. So C will move towards C3, A to A2, and B acts as pivot. So the effective displacement of the flapper after a full operation is this minus this plus this. That is the effective displacement of the nozzle. Now we should derive the mathematical model of this PI and again PID controller for motion balance type. So this is the effective or net deflection of the flapper towards the nozzle direction. You may try to solve this problem at your own hand to find the expression for PI controller. But we will in our next class we will explain this mathematical model of this motion balance type PI controller. Before that, you may try to solve this, derive this mathematical model for motion balance type PI. PID is just the similar type, only the derivative action will be added over the PI. So if you can derive the motion balance type mathematical model of motion balance PI controller, that is enough. But the final expression, that means the output, should exactly tally with the model of PI controller. So in next class we will try to solve the PI controller model as well as the only one method we have left, that is force balance type pneumatic controller. So thank you for today's class.